In the last class, we started the discussion on alcohols and learned some of the physical and chemical properties of these molecules. We were discussing the different synthetic routes to making these compounds, starting from alkenes as substrates, and there we saw that how the monohydric alcohols can be obtained from the alkenes either through a Markovnikov pathway or an anti-Markovnikov pathway. So, continuing on with the last time discussion, we again start with olefins and see some of the other strategies for making different types of alcohols with olefins as substrates. So far we talked about the preparation of monohydric alcohols starting from olefins. Today we will learn how we can make the dihydric alcohols also starting from olefins as substrates. So, the synthesis of dihydric alcohols, which we say what we will be making are vicinal 1,2 diols. So, we will be making vicinal diols or 1,2 diols starting from alkenes. So, the general strategy for doing this, what we say is an oxidation reaction. So, it is an oxidation with different kinds of oxidizing agents like a KMNO4, aqueous, cold, alkaline KMNO4 solution. It could be an osmium tetroxide in combination with a peroxide under basic conditions, right. So, we are going to study some of these strategies for making the vicinal diols. The general scheme for the alkaline KMNO4 dihydroxylation can be shown like this, that if you start with any olefin and you treat it with cold aqueous alkaline KMNO4, it gives you a diol. It gives you a 1,2 diol, and this diol is a cis diol. So, this is the specificity of this reaction in terms of the stereochemistry, that the diol which you get is a cis diol. So, what is the reason? How does this reaction execute? So, exemplifying it further, let me show you that if you start with any substituted olefin, treat it with KMNO4, alkaline, cold. Cold is very important, because if the temperature rises, if we heat the reaction up, then the diol which is going to be generated is going to cleave at the 1,2 position to give you a degradation product. So, once you form this diol under cold conditions, so this is a cis diol on the same side of the double bond, both the hydroxyls on the same side of the double bond. If you do the same reaction at high temperatures, then this is going to lead to the cleavage of the carbon-carbon double bond and give you an oxidative degradation product. So, it is going to yield oxidative degradation products. So, that is why it is essential that we carry out these reactions under cold conditions. The reaction is very selective. If you start with a cyclic olefin like a cyclohexene, you get a syn diol which tells you that this is a cis or a syn diol, which tells you that the reaction is highly stereospecific. If you start with a butene, let us say a trans butene, you start with a trans 2 butene and you subject it to aqueous alkaline KMNO4 solution, you get a diol which is again a syn diol, which means that both the hydroxyls are adding from the same side of the double bond, which could either be above the plane or they could be below the plane, which means that you get a pair of enantiomers, you get a DL mixture, you get a racemic mixture of the two products. So, this is when the case with trans 2 butene. If you take the other isomer of butene, that is the cis 2 butene, if you start with cis 2 butene and subject it to dihydroxylation under the same conditions with alkaline KMnO4, you get the diol, the syn diol with both the hydroxyls adding on to the same side of the double bond, and what you get eventually you will see is nothing but a meso compound. So, you get a meso compound if you start from a cis 2 butene. So, let us look into the mechanism of the reaction, how does it operate in giving us a syn stereochemistry. So, when you start with any olefin and you treat it with permanganate. So, the first step is the attack of this pi electron of the olefin onto this permanganate to give you an intermediate which is a cyclic intermediate. So, this is a syn dihydroxy which you are going to get eventually, and you get this cyclic manganate ester intermediate. So, you get this manganate ester cyclic intermediate which on subsequent hydrolysis with the sodium bisulfite gives you the corresponding diol, that is a cis diol. Okay. So, this is the mechanism of the KMnO4 dihydroxylations to give you from the olefin we are getting the vicinal diol, the 1,2 diol. The same strategy can also be used using another reagent that is called osmium tetroxide. So, just the way KMnO4 works, we can carry out the same reaction using osmium tetroxide, and this works more or less in the same way to give you the syn addition products forming a similar cyclic intermediate as was being generated by KMnO4. So, here what you get is this 5 membered osmate ester intermediate which undergoes hydrolysis to yield the vicinal 1,2 diol with a syn selectivity. So, in this case generally what we do is that along with this diol, your osmium is recovered in the form of osmic acid. So, you get this osmic acid which is the reduced form of your OSO4 which we started with. So, you get the osmic acid, the reduced form which is further reoxidized in the presence of the co-oxidant TBHP which had been added to the reaction mixture. So, TBHP works as a co-oxidant and oxidizes the osmic acid back to OSO4. So, these are the two reagents which carry out the syn dihydroxylation of the olefins. All right, moving ahead, we have another interesting way of making the diols starting from the epoxide which can be generated with the help of peracid. So, with the help of peracids, we can again get the diols, and this is called the peracid oxidation. So, the starting point is the same. You begin with the olefin, you treat the olefin with a peracid. This is the first step, and the second step, once you treat it with the peracid, you get an intermediate which is an epoxide, and this epoxide once you get, the second step is to treat this epoxide with an aqueous acid solution when you get your diol. And the interesting thing about this reaction is that the diols which you get are trans diols. Unlike the previous two cases where we were getting the cis diol, in this case we get trans diol as the major product. So, the peracid could be any of the acids like a performic acid. So, you can have any of these peracids, you can have a performic acid, you can have a perbenzoic acid, okay. You can have a perbenzoic acid which would be C6H5CO2OH. You can have a perphthalic acid, okay. You can have a perphthalic acid. So, any of these per acids can be used. The first step to bring about the epoxidation, and second step is the ring opening of the epoxide in the presence of the aqueous acid. So, let us see how the scheme looks like for this reaction. So, you start with the olefin, treat it with the per acid, and you generate an epoxide. So, this epoxide which you are generating, the first step, this is a concerted first step, and the addition of the per acid follows a syn addition pathway, and you get what we call as a cis epoxide. So, the first step is a syn addition of the performic acid onto the olefin to give you an epoxide, and this is followed by hydrolysis with aqueous acid. So, you can have either an aqueous acid, or you can have even a methanolic HCl, any of these reagents can be used. So, any type of nucleophile. So, you use an aqueous acid and you are able to open up this epoxide ring to give you 1,2 diols which are trans in their relationship with each other. Okay, so let us understand the mechanism of this oxidation. If you start with an unsymmetrical olefin, and you treat it with the per acid, so the first step is the epoxidation, which is a cis addition. So, you get the corresponding epoxide through this pathway, which is a cis addition pathway. The next step, which is the ring opening of the epoxide. So, the ring opening of the epoxide to give you the corresponding diol if your nucleophile happens to be water molecule. So, the general mechanism which goes for this is that you start with the epoxide, and carry out the hydrolysis in presence of protonated solvent, which is water in this case. So, the first step is the protonation of the epoxide to give you this species in which the oxygen gets protonated. This is the first step, and this can be seen also in terms of the partial weakening of this carbon oxygen bond, this bond lengthening, and the positive charge residing on the carbon which is more substituted. So, the positive charge goes and sits on the carbon which is more substituted carbon of the initial original olefin. So, once this happens, the next step is the attack of the nucleophile. So, the nucleophile comes and attacks this carbon which is bearing this positive charge. So, the nucleophile could be anything, it could be water or it could be any other nucleophile which opens up this oxirane ring. So, when the nucleophile is water and it opens up this ring, we expect so, when this attacks here and the ring opens up, we get this trans diol in which the hydroxyl or the nucleophile, it goes and attaches to the carbon which is more substituted. So, this is important when you have an acid catalyzed ring opening of the epoxides that the nucleophile goes to the carbon which is more substituted, is the preferred pathway for its action. Okay, so going ahead from here, these were the methods by which we can synthesize the diols as well as the monohydric alcohols starting from alkenes as substrates. Now, we will see the other starting materials that can be used to prepare these molecules. One of these which was introduced to you last time was alkyl halides. So, we can start from alkyl halides for making alcohols through a nucleophilic substitution reaction. So, you start with alkyl halides and you can treat them with a nucleophile like a hydroxide anion to give you alcohols, and the halide is lost as a leaving group. So, there is essentially what happens is that you can carry out the hydrolysis of the alkyl halide with either aqueous alkali or moist silver oxide to give you the corresponding alcohols. We can also do the same reaction starting from a chlorohydrin as a substrate. So, you can, if you want to again make the diols, you can start from a chlorohydrin and carry out its hydrolysis under slightly basic conditions, when you would end up getting a diol which is nothing but an ethylene glycol. And if you want to recollect what is the method of making these halohydrins, a chlorohydrin in this particular case, you have to again start from an olefin. If you want to make a chlorohydrin, you start from an olefin and you treat it with chlorine in the presence of water. So, you are able to generate a chlorohydrin which can further be hydrolyzed to give you the ethylene glycol. So, this is another substrate for making the alcohols. The next one could be an ester. So, esters can also be used for generating alcohols. We know how esters are formed. Esters are formed by the condensation between an acid and an alcohol, and we do just the reverse reaction of the same. So, if you start with an ester, you treat the ester with water. So, we are doing nothing but we are doing the hydrolysis of the ester, and this is generally catalyzed either in the presence of an acid or a base. So, it is an acid or a base catalyzed hydrolysis of the ester which we perform, and we get the original starting components, the acid and the alcohol from which this ester was generated. So, the esters can be subjected to an acid or a base catalyzed hydrolysis to yield the corresponding alcohols. Okay. Going further, the importance of this strategy can be visualized if I show you that if you take any ester which is having an alcohol that is a tertiary alcohol. Okay. So, suppose you take this ester in which it is a tertiary alcohol and you carry out the hydrolysis again under acid catalyzed conditions, you end up with the acid and the corresponding tertiary alcohol, which in this case happens to be a tertiary butanol, and this particular method is a very effective way of getting tertiary alcohol starting from the ester. So, this tertiary alcohol again obviously was made starting from the corresponding tertiary alcohol and the silver salt of this acid, the halide of the corresponding alcohol. So, you can start with a tertiary butyl chloride and treat it with the silver salt of the acid, you get this ester, and this ester can be hydrolyzed to give you back this tertiary alcohol which happens to be butanol in this case. So, this is a very important strategy for making these tertiary alcohols. The other starting substrate which we can think about is an ether. So, ether, the general way we represent an ether is with the ROR dash. If we carry out the hydrolysis again, so what do we want? This ROR has to be converted to ROH. So, what comes to our mind is that you have to carry out the hydrolysis. So, hydrolysis under what conditions? Again it is the acid catalyzed, the presence of dilute H2SO4 under pressure. So, when we do this, we are able to get split this alcohol, split this ether into the corresponding two alcohols. So, these are some of the other starting substrates which can be used for making alcohols other than olefins. Let us look at now the one of the most important class of compounds for making alcohols, that is the carbonyl compounds. Carbonyl compounds has a huge substrate scope, it has a very huge versatility. So, the carbonyl compounds can be converted to alcohols. These alcohols can be 1 degree, 2 degree, 3 degree. So, if I have to show a general scheme, I can say any carbonyl compound can be converted to the corresponding alcohol. What we are doing in the process is we are adding 2 hydrogen atoms. That means, we need some source of hydrogen which can come from any reducing agent. So, we need a reducing agent to carry out the reduction of the carbonyl compounds to the corresponding alcohol. So, these reducing agents can again be very many. There is a huge list of reducing agents which can be employed to carry out the transformation of a carbonyl compound to an alcohol. We can use a hydrogenation system like a hydrogen in the presence of any transition metal catalyst like a nickel or palladium. So, this can be used for hydrogenation. This system essentially is very powerful for carrying out a olefin reduction. So, a carbon-carbon double bond is reduced very effectively, and a carbonyl can also be reduced under slightly more harsh conditions as compared to an olefin. So, you can have a hydrogenation unit like a hydrogen with a metal. You can have sodium alcohol. Sodium alcohol is used to carry out the reduction of esters into alcohols, typically to convert esters into alcohols, and for this particular reagent we have a name reaction which we call as the Bouvelt-Blanc reduction. So, the reduction of esters to alcohols using sodium alcohol is called the Bouvelt-Blanc reduction. We can also have another reagent which we call as aluminium isopropoxide. Aluminium isopropoxide in isopropanol. This is another reagent which is used to carry out reduction of carbonyl compounds, and it also has a specific name what we call as MPV reduction, that is based on the name of these people, Meerwin, Pondorf, Worley reduction. This is a very cheap method of carrying out the reduction because it is using a cheap reagent like the aluminium isopropoxide, and isopropanol is the sacrificial alcohol which is used in this reaction. So, the overall reaction is that if you start with any ketone, this is for the reduction of these ketones, you start with any ketone and you treat with aluminium isopropoxide in the presence of isopropanol. So, you have isopropanol. So, what you get is the corresponding reduced alcohol. You get the corresponding alcohol along with the generation of acetone. So, your isopropanol is converted to acetone. This is what is the sacrificial alcohol which is giving away its hydrogens to the carbonyl system. So, there are very many such reducing agents which can be used to convert carbonyl compounds to alcohols. Another important class of these molecules which can be used as reducing agents, we call them as mixed metal hydrides. Mixed metal hydrides, as the name says, it is a mixed and a metal. So, which metal and why is it called mixed? So, we will discuss 2 important reagents under this mixed metal hydrides. One is a lithium aluminium hydride and another is a sodium borohydride. So, 2 of these mixed metal hydrides are used to convert carbonyl compounds to alcohols. Both of them are different, they have different reactivities, they are different in terms of their reactivities, and when I say they are different in terms of their reactivities, automatically there becomes a difference in the selectivity as well, because we know that anything which is more reactive becomes less selective and anything which is less selective is more reactive. Okay. So, when we compare the two, lithium aluminium hydride and sodium borohydride, the general comparison is that a lithium aluminium hydride is a stronger reducing agent and it is more reactive than sodium borohydride. Okay. It is stronger, it is more reactive and therefore, it is less selective as compared to sodium borohydride. So, when we say that it is less selective, what are the different classes of carbonyl compounds it can reduce? It can reduce a range of carbonyl compounds going from an acid chloride to an aldehyde to a ketone to an ester to an amide to an acid, a nitrile and an epoxide also. So, it can reduce a range of different functional groups which sodium borohydride cannot. And if I compare what is the reactive order in which it reduces these different functional groups, I can come up with this series in which I can claim that acid chloride reacts the fastest compared to formaldehyde, which is higher than the corresponding aldehyde, which is more than the ketone, ketone is more than the ester and then this is followed by the amide followed by the carboxylic acid. So, this is the order in which the different carbonyl compounds will react with lithium aluminium hydride, but of these not all react with sodium borohydride. Sodium borohydride can only reduce up till ketone. So, it can reduce an acid chloride, an aldehyde or a ketone. So, this is what a sodium borohydride can do. It cannot reduce an ester, amide or an acid which a lithium aluminium hydride does. So, what is the reason? Why is there a difference in the reactivity between the two? Let us understand this in terms of their structure and their bonding. So, a lithium aluminium hydride, if we analyze the lithium cation is a very small cation, okay, and compared to sodium. So, it coordinates to the carbonyl oxygen and activates this carbonyl oxygen electrophilicity. So, it helps in increasing the electrophilicity of the carbonyl carbon, okay, and therefore, it makes it more reactive. So, in general it is a stronger Lewis acid and it makes the carbonyl more reactive. So, that is one of the ways in which this can be explained, that why lithium aluminium hydride is a stronger reducing agent than sodium borohydride in terms of the cation aspects, that means lithium versus sodium, that lithium is more favorable in increasing the electrophilicity of the carbonyl carbon compared to sodium and therefore, it is more reactive. So, this could be one of the explanations. The other explanation could be in terms of the electronegativity difference between aluminium and boron. So, if we see that the electronegativity of boron is roughly of the order of 2, then that of aluminium is of the order of 1.5. So, clearly since boron is more electronegative than aluminium, what it is going to do? It is going to hold that electron pair which is sharing with the hydrogen more towards itself. So, when it is more towards itself, it is less available for donation as in the form of a hydride and therefore, it is a weaker reducing agent as compared to the lithium aluminium hydride. The third explanation could be in terms of the bond length and the sizes of aluminium and boron. So, aluminium is larger than boron in terms of their size. So, if we see the ALH and the BH bond lengths, or in other words, if we compare the orbital picture. So, aluminium and hydrogen, it is the 3 sp3 of aluminium which is going to bond to the 1s of hydrogen, and when we look at boron and hydrogen overlap. So, boron and hydrogen, the overlap is between the 2 sp3 and 1s. So, overall the effect is that this aluminium hydrogen bond is longer. It is longer and the boron hydrogen bond is shorter relatively. Therefore, this is stronger, this is weaker, and since it is weaker, it is more reactive. It is more reactive and it is more diffused electron density. So, it is more diffused, this is stronger, this is less reactive. So, these are some of the explanations which can be understood to distinguish between the reactivity patterns of lithium aluminium hydride and sodium borohydride. Now, the other question could be, why at all do we have to use a sodium borohydride? Why can't we simply use a sodium hydride as the hydride transfer reagent? Never do we see sodium hydride being used as the hydride transfer reagent. So, there must be some reason associated. Let us try to see why it is. So, sodium hydride cannot be used as a nucleophile. Okay, it is not a good nucleophile, however, it is a good base. Sodium hydride is only used in the form of a base, it cannot be used as a nucleophile because the 1s orbital is too small to interact well with the carbonyl carbon. So, with the carbonyl carbon it cannot interact well because of its very small size, and therefore, it is not good to be used as a nucleophile, it only works as a base. Okay. So, with this understanding, let us see what are the different kinds of reductions that can be exploited by making use of these two reducing agents. So, if you look in general, the conditions under which the two operate are typically not the same. So, if you have an aldehyde, okay, and you treat it with lithium aluminium hydride. So, the first step which involves lithium aluminium hydride as a reducing agent, it has to be carried out under dry conditions. So, you have to have a dry ether, a dry THF for carrying out this reaction. So, the first step is the reduction which gives you the corresponding alkoxide anion. So, the first step involves the formation of this alkoxide anion. This is the first step, okay, and this is followed by the second step which is the workup and involves the reaction with any proton source. So, you can have aqueous protons medium. So, it has to be an aqueous workup. Essentially, you need a proton source to be delivered to this alkoxide anion which gives you finally this alcohol. So, the question now again that can be posed is, why can't we put this water right in the first step along with LAH? Why do we have to do it sequentially in the second step? So, subsequently it is added because lithium aluminium hydride, as we just saw, is a very reactive compound. It reacts. So, if you look at the structure, the lithium aluminium hydride is quite reactive, and if it finds water in the vicinity, okay, this is going to just pick this up and give you hydrogen gas. So, there is a very explosive reaction, it can result in the evolution of hydrogen gas along with formation of these entities. So, because of this, the reaction has to be carried out under dry conditions, and we cannot use water directly as a solvent when we are carrying out reductions with lithium aluminium hydride. Okay. Going ahead, let us look at the mechanism which is involved in these hydride reductions with lithium aluminium hydride. So, we are starting with the carbonyl compound, and let us take a general reaction which is the reduction of an ester in this case. So, we said that lithium aluminium hydride is very strong and it is capable of reducing an ester into an alcohol. But mind you, for this we have to take an excess of lithium aluminium hydride. We cannot take stoichiometric because then the reaction will not go up till completion, which involves the complete reduction of ester to alcohol. So, when we do this, what is the mechanism that is involved? So, you start with the ester, you add lithium aluminium hydride. Okay. So, the first step could be the transfer, the activation of this carbonyl and the transfer of this hydride of the lithium aluminium hydride onto the carbonyl. So, there is activation of carbonyl and there is transfer of the hydride. So, the first step is the transfer of the hydride and it results in the formation of this kind of an intermediate. So, you get a tetrahedral intermediate. This tetrahedral intermediate now can further collapse with the loss of this alkoxide anion to give you an aldehyde. So, you get an aldehyde from this intermediate and the next step would be repetition. So, just the way an aldehyde would be reduced by lithium aluminium hydride, the same thing happens. You again have the lithium aluminium hydride sitting there in the system and it reacts with the aldehyde which is generated one more time and it gives you the corresponding intermediate, which now transforms to this intermediate and then can be quenched in the presence of any proton source to give you the corresponding alcohol. So, as you can see, we started with an ester, we have got an alcohol and there is addition of 2 atoms of hydrogen. So, 2 hydrogens have added through the lithium aluminium hydride, both are coming from LaH. So, that is why we have to add excess of LaH to ensure that the reaction goes to completion. So, there is twice the addition of LaH onto the carbonyls, whether it was starting from an ester or it was an intermediate aldehyde. Okay, so, now let us see what happens in case of sodium borohydride reduction and how it is different from a LaH reduction pathway. Sodium borohydride is water soluble, okay. Unlike lithium borohydride, it does not react with water violently. So, it is water soluble, tetrahedral, BH4 minus anion, and in this case the role of sodium ion is not very important as was in the case of the lithium ion which was responsible for activating the carbonyl carbon. So, in this case does not happen. So, the first thing is how does it exist. So, your BH4 minus anion is a tetrahedral anion in which boron carries the formal negative charge. So, if boron carries the formal negative charge, one could ask that why does it not directly go and react with the electrophile. So, you have an electrophilic carbon, why does boron not go and react on its own with the electrophilic carbonyl carbon and give you this kind of an intermediate. However, we say that this particular pathway is not possible. It is not possible. In this case, the boron is becoming pentavalent. It is extended its valency becoming pentavalent. It is not feasible, and so what happens, the other pathway which boron in the form of BH4 minus chooses is that it gives away this hydrogen in the form of the hydride ion to the electrophile. So, it does not react through the boron center, but it gives this hydrogen to the electrophile with the electron pair, and what we get in the process is a borane with boron having an empty p orbital, and the electrophile picks up this hydrogen as a hydride. So, this is what happens during the reduction with sodium borohydride as the reducing agent. So, if you start with any ketone or any carbonyl compound like an aldehyde or formaldehyde or an acid chloride, the first step, sodium borohydride, is always used in presence of any protic solvent. It is very important to have a protic solvent in the medium for carrying out borohydride reduction. So, the first step here is okay. So, the first step would be that your borohydride it attacks this carbonyl carbon, okay, and this carbonyl carbon is not forming a very strong coordination with the cation sodium. There is a weak interaction, and there is also a weak interaction with the protic alcoholic solvent, which is also coordinate from this oxygen to the boron site. So, this is the first step in which there is a transfer of hydride followed by picking up of the proton from the solvent to give you the corresponding alcohol, and you get this anion which can still act as a reducing agent. So, there are still 3 more hydrides available to it to react 3 more times with any of the carbonyl compounds, and it acts further as a reducing agent. So, this is how the mechanism of a lithium aluminum hydride reduction is different from that of a sodium borohydride. Okay, going ahead, let us see some of the differences in terms of the chemoselectivity of reductions between these molecules. The lithium aluminum hydride versus sodium borohydride, how do they differ in terms of their reactivity, which is implicated in the chemoselectivity of reduction. So, if you start with any substituted benzaldehyde, let us say this benzaldehyde has an ester functionality to itself, you treat it with sodium borohydride in ethanol, or you treat it with lithium aluminum hydride followed by protonolysis. The expected product would be in both the cases the reduced aldehyde for sure. So, what we get when we take a sodium borohydride, we get the corresponding alcohol by the reduction of the aldehydic carbonyl, but the ester functionality remains untouched. So, this ester is untouched, it still is there in the molecule, but when we do the reduction with lithium aluminum hydride, since it is a very strong reducing agent, we cannot control the reduction up till this step. So, it cannot be stopped till the reduction of the aldehydic carbonyl. The reaction also reduces the ester functionality which is available in the molecule, and you get here a primary alcohol generated from the ester, and we just saw the mechanism of reduction of ester with lithium aluminum hydride. So, this is the kind of chemoselectivity which resides in the reduction of LAH versus sodium borohydride. Let us see a few more examples. What happens when we have conjugated carbonyls? So, if you have any such alpha beta unsaturated carbonyl system and you treat it with sodium borohydride and you treat it with lithium aluminum hydride, is there any difference in the products, or do we get identical products in both the cases? So, when you treat it with lithium aluminum hydride, the product which you expect to get from here is the carbonyl reduction product, that is this alcohol, which you can see is a allylic alcohol. So, this is, you can see this is an allylic alcohol. So, this is an allylic alcohol, and if you do a reduction with sodium borohydride, right, the product which you get is this. So, if you just see what is happening, what is the difference? So, in a lithium aluminum hydride you get a 1,2 addition product. It is nothing, the reduction is nothing, but it is a nucleophilic addition of the hydride onto the carbonyl. So, your nucleophilic addition of hydride on the carbonyl is your reduction process with these mixed metal hydrides. So, in the case of lithium aluminum hydride you get a 1,2 addition product, but when you do reduction with sodium borohydride what you get is a 1,4 addition. Okay, so, if we just number it 1, 2, 3, 4, what you get here is a 1,4 addition product, and you get a 1,4 addition product, and this can subsequently rearrange to give you the 3,4 addition product. So, this is the difference between the reduction of alpha beta unsaturated carbonyl compounds with LAH versus sodium borohydride. In LAH you get a 1,2 addition which is the reduction, and in case of sodium borohydride you get a 1,4 addition, which apparently seems to be a 3,4 addition product. If you look at a cyclic ketone alpha beta unsaturated cyclohexenone, you treat it with LAH, you treat it with sodium borohydride. Try to write yourself the products which are generated. If I say LAH gives you 1,2 addition, so the expected product would be this allylic alcohol, and when sodium borohydride gives you a 1,4 addition reduction pathway, the product which you will get is this enol, which can stabilize to the more stable keto form, and you get the corresponding cyclohexenone as the product. So, this is how the two show difference in their reactivity patterns, the chemo-selectivity with the carbonyls. Reduction of carbonyl compounds not only with the hydride sources, but with alkyls which are bearing a minus charge. So, we are talking about the carbanions. If we can treat the carbonyls with the carbanions, what is the source? So, you want to treat a carbonyl with a carbanion which can again undergo a nucleophilic addition and give you these kinds of molecules. So, the first thing which comes to our mind for a source of an alkyl bearing a negative charge is the Grignard's reagent. So, the reaction of the carbonyl with Grignard's reagent or the closely resembling alkyl lithiums. So, the Grignard's reagent and alkyl lithiums can be used again to reduce the carbonyls into the corresponding alcohol. So, a Grignard's reagent, as we all know, is a molecule in which a carbon is bonded to a magnesium. So, this is carbon which is more electronegative, and this is magnesium which is less electronegative. So, therefore, this bond pair of electrons is going to reside more towards carbon, and therefore, the carbon has this character of behaving like a carbanion, because this electron, the bonded electron pair between the carbon and magnesium, it resides closer to the carbon. So, we get these Grignard's reagent which can be synthesized starting from alkyl or aryl halides, and you treat them with magnesium turnings under dry conditions with a dry ether as a solvent, and what you get is the CMGX bond forming, and this is what was discovered by Victor Grignard, for which he received the Nobel Prize in 1912. Okay, so, we are going to make use of this as the reagent for reducing our carbonyl compounds to the corresponding alcohol. So, these are very powerful reagents for making the carbon-carbon bond. So, carbon-carbon bond formation with the help of the Grignard's reagent is a very, very useful strategy in organic synthesis. You start with the Grignard reagent, treat it with the carbonyl in dry ether. So, the first thing which is going to happen is the nucleophilic addition of this alkyl group onto the carbonyl carbon, and you get this intermediate, which can then be hydrolyzed to give you the corresponding alcohol. So, this is a very powerful strategy, because depending upon the carbonyl you start from, you can get a range of alcohols which could be 1 degree, 2 degree or 3 degree alcohols. So, if you start with something like a formaldehyde and treat it with methyl magnesium bromide followed by hydrolysis, you get the corresponding 1 degree alcohol. If you start with an aldehyde instead of formaldehyde, any other aldehyde, and employ the same conditions with the methyl magnesium bromide, you end up getting an alcohol which is now disubstituted, it is a 2 degree alcohol. If you do the same thing on a ketone, okay. So, since it is already disubstituted, and when you add another alkyl group to the carbonyl of the ketone, you end up getting an alcohol which is a 3 degree alcohol. Not only to the acyclic systems, it works with cyclic systems as well, and you can very well get the derivatives of cyclohexanol. So, this is a very, very powerful strategy for making 1 degree, 2 degree, 3 degree alcohols. The general method for this would be very straightforward, that is the nucleophilic addition of the alkyl group of the Grignard's reagent onto the carbonyl carbon to give you an intermediate, in which now this oxygen is bearing a negative charge, and this picks up the proton and you get your desired alcohol very conveniently. The only problem here is that handling of the Grignard's reagent is not so simple and needs some practice and sophistication. Okay, you can also make use of esters. So, just the way your lithium aluminum hydride was being used in excess to convert an ester into an alcohol, in the same way a Grignard's reagent when used in excess can convert an ester into an alcohol. So, let us see how. If you start with an ester and you treat it with Grignard's reagent followed by acid hydrolysis, you get the corresponding alcohol which is a 3 degree alcohol. Okay. So, in this case you are getting a 3 degree alcohol. With the lithium aluminum hydride you were getting a 1 degree alcohol, because what was adding was a hydride, and now what is adding is a alkyl group with the electron pair. So, the mechanism which goes for this ester addition of the Grignard's reagent onto the ester is more or less the same as was for lithium aluminum hydride. Okay. What you get here, okay, so if I put this as R dash, what you get here is a which undergoes loss of alkoxide to give you the corresponding ketone, and then there is addition of another molecule of Grignard's reagent onto the ketone, and this furnishes the corresponding alcohol. Okay, so I stop here and will continue more discussion in terms of the reactions of these alcohols next time.